Now we're going to learn about how this same idea of proportion and rate of change applies to chemistry. Oh, I must have some fans of chemistry in the audience. That's good. Example 5, radioactive decay example above. That's the one we looked at back, one more, here. Applies if one chemical breaks down into another proportional to the amount of chemical present, and that's an example of a first order reaction, and this is exactly like example 2 above, so I need say no more about that. But suppose we have two chemicals, call them chemical A and chemical B, that are combining to make some other chemical, chemical C, at some particular rate. The rate of change of chemical C is a product of the remaining amounts of A and B. And this is what's called a second order reaction. Note that it's a first order differential equation and is not linear, but looks like it might be separable. We'll learn actually in another lesson, this might be a really good example of what's called a Bernoulli equation. Anyway, if X represents the amount of chemical C, and A and B are the original amounts of chemical A and B, then the model looks like this. The change in chemical C with respect to time is proportional to the amount of chemical A that's left, that's A minus the amount that's been changed to chemical C, times the amount of chemical B that hasn't yet been changed into chemical C. So A minus X and B minus X are representing the remaining amounts of A and B respectively.